Now let's look at the energy aspect of the force of gravity. We learned before that the weight of an object, which is basically the gravitational attraction of the Earth on that object, is a conservative force. So it shouldn't be a surprise that if you extend this beyond just the weight of an object near the surface of the Earth, but to all gravitational force, you should expect this also to be a conservative force. And we have the ability to prove that for this arbitrary force going beyond the vicinity of the Earth. Suppose I have this object, all right? It moves along an arbitrary path from this initial position right here to a final position right there under the influence of gravity of, say, the Earth, all right? So as it moves from initial to final along this arbitrary path, the magnitude and direction of the force of gravity, F sub g, keeps on changing. All right, now, how much is the total work done by the force of gravity as the object goes from initial to final? If we can show that this amount of work is independent of the actual path, but it only depends on the position initial and position final, then we can see that this is indeed a conservative force, as we should expect. All right, now, the work done in moving along a very infinitesimally small distance, ds, is fg dot ds, right? Fg dot ds. So I'm going to write that down. So dw, the infinitesimally small amount of work done by gravity, equals to fg dot ds. Okay, fg, as you can see, points from the object to the center of the Earth. It could be any other object for that matter. But ds is arbitrary. Okay, so the angle between fg and ds can vary all the time. Now, we took this part of the diagram, and we extended it. We blew it up to that size so we can see it more easily, right? So let's take a closer look at what happens when the thing moves by an infinitesimally small amount of displacement ds from here to there. During that time, it is subject to a force of Fg. Since ds is very, very short, you can think of Fg as a uniform constant force during this entire movement of ds. Okay, it points to the center of the Earth. Right? Let me use a unit vector r from the center of the Earth to the object, and that's the direction of a unit vector r here. Now, ds has an arbitrary direction, but I can always break down ds into two components. One is along the radius, along the line connecting the center of the Earth and this object. Okay, the object is right here. The object is right here. Okay, the center of the Earth is somewhere down there as the force of gravity points towards. Okay, and ds breaks down into two components. This green component, okay, this one is along the line connecting this object and the center of the Earth. So here is this green component, right? And then you have a blue component that is perpendicular to the green component. Here's the blue component. Now, when it comes to the work done, it is only one of these two components that you have to consider. Which component would that be? Would that be dr, right? Because dr perp, it's perpendicular to the direction of the force. Therefore, fg dot d perp is 0. So you have to consider that. Okay, it is only the dr you have to consider. So I can rewrite the force, the work done by the force, as fg dot dr. Okay, now fg has a direction that's opposite to the unit vector r, right? So let me write down what that fg is. It is g times the mass of the Earth times the mass of this object divided by r squared. That's the magnitude, and the direction is simply negative r. Okay? Negative r. That is fg dot dr. Dr is this vector right here. Okay, it's this vector right here, and you can clearly see dr has a direction that is in the unit vector r. Okay, the magnitude of dr, I'm going to write it down as just dr. Okay, and the direction is this, is the direction, right? So you see, I can finish the dot product here. There are two vectors, negative r and r, both are unit vectors. And then what is negative r dot r? Well, r dot r equals 1, right? You know, both of these two unit vectors have unit magnitude, therefore r dot r equals 1. And don't forget there's an overall negative sign. You can negative g m m over r squared dr. Okay, dr is not the same as ds. Dr is only the movement along the line connecting the object and the center of the Earth. Okay, it's the radial movement. And that's the only movement that counts when it comes to work done. So how much is the total work done? W from initial to final. What is that equal to? Well, that is equal to the integral of over dw. And let's work that out. I'm going to take these constants out. Okay, gmm. And then 1 over r squared dr going from r initial to r final. Okay, r initial is initial distance between the center of the Earth and the mass in question. R final is the final distance. All right, now we can easily finish this integral, right? And the answer turns out to be negative g m m over r initial, then plus g m m over r final. Okay, now let's say r initial is less than r final. As you can see from this diagram, we look at the case when r initial is less than r final. So basically the object is moving away from the Earth, right? In moving away from the Earth attracts it, the Earth wants to pull it in. Therefore, the work done by the gravity of the Earth would be negative in this process. Okay, now is that true? Well, look at this final expression here. The first term is negative, the second term is positive, but the first term has a smaller denominator, r initial. The next term has a greater denominator, r final. Therefore, the first term has a greater magnitude than the second term, and it's negative. So therefore, the overall work done would be negative, which makes sense. Okay. Now, on the other hand, we realize that in this final expression, there is no specific information about the actual path. You know, this arbitrary path that led us to from initial to final. Okay, this path here. The details of the path does not matter. What matters is only r initial and r final, which have to do with initial and final position, like r initial and r final, right? There's no mention about how it went from r initial to r final. Okay, so therefore, this force indeed is a conservative force, as we expect. So we can define this as what? Ug initial minus Ug final. Recall the definition of potential energy. For a conservative force, you have U initial minus U final equals what? The work done by that force from initial to final, if it's a conservative force, right? That's exactly what we have defined the gravitational potential energy as. Okay, U initial minus U final. That's the general expression. Okay, so what is Ug initial? What is Ug final? Well, you can find a correspondence here. Here's initial corresponding to initial, and here's final corresponding to final. And so you can relate Ug initial, let it equal to negative gmmr initial over r initial, and let Ug final to be negative gmm over r final. So in general, you can then write Ug as a function of r. That r is the separation between the two masses in question, as negative g first mass times second mass over r to the first power, not the second power. Okay, this is not the same thing as a force. This is the gravitational potential energy. So this is what we come up with, right? I mean, this doesn't look like mgh, you know, what we know before. But we'll fix that problem, okay? Now, by the way, this is not the only possible expression for the gravitational potential energy. You can add a constant, okay? You can actually add a constant to it. That shouldn't be a problem. You add a constant. Because, you know, always add a constant to any potential energy. As long as that's the same constant for initial and final, they're going to cancel out. Okay. Now, how does that compare with something we already know, which is MGH? That looks very different again. Okay, so let's see how we can come up with an agreement between this new expression for gravitational potential energy, which is obviously more general, and our old expression for MGH for the gravitational potential energy near the surface of the Earth. So let's take a look at what happens to an object that's placed near the surface of the Earth. The altitude of the object from the surface of the Earth is called h. Okay, so here's where the object is right here. Distance h above the surface of the Earth. The radius of the Earth is considered, is denoted as the capital letter R. We assume that h is far less than R, so that's why we say it's close to the surface of the Earth. What is the gravitational expression, gravitational energy expression for that object? Now we know from what we learned before, it's MGH, or more precisely MGH plus a constant, which we always often set up to 0. How does that agree with this totally new looking expression for the potential energy, negative GMM over R? Well, let's see here. Let's see if we can derive from this general expression here to find the old familiar expression for MGH in this special case. Okay, now, so we have from general expression UG, okay, at R. That's negative G times the mass of the Earth times the mass of the object divided by R, right? And R is big R plus H, of course. Big R plus H. Now, big R is much, much greater than H. So let's see how we can take advantage of this approximation. What I'm going to do is I'm going to factor out the big R first. Okay, I'm going to factor out big R. So it is negative G M M over big R. I'm going to take that out. And what's left is this, is 1 divided by 1 plus H over R, right? Now, still doesn't look like MGH, but don't worry, it's coming up. Okay. First of all, the expression in front of the parenthesis, this expression right here. If I multiply both the numerator and denominator by an extra factor of R, that becomes R squared. Okay. And then you have another R here. What do you think we'll be getting? What is GMM over R squared? Actually, what is GM over R squared? What is this part? GM over R squared. Well, GM over R squared is actually mg. Do you recall that? Because the force of gravity exerted on an object of mass m on the surface of the Earth, isn't that equal to mg? But it's also equal to g times mass of the Earth times mass of this object over R squared. Right? So you see GMM over R squared, isn't that the same as mg? So let me replace this with negative mg times R. Okay, that makes things a little bit simpler here. And what's left is this, whatever this thing is in a parentheses, 1 over 1 divided by 1 plus H over R. Now H over R is a lot less than 1. So we define it, we call it X. A whole lot less than 1, okay? And with that, I have this expression in a parenthesis, 1 plus H over R to the power negative 1. Okay, this is what's in the parenthesis. This is the same as 1 plus X to the power negative 1. Okay, at this point, I'm ready to take advantage of this approximation of X far less than 1. You have a general mathematical formula, 1 plus X to the power n. When X is very close to 0, it is equal to roughly 1 plus nx. Okay, this in fact is a well-known approximation. We use that very often in physics. I'm sure you have learned that from a math class. In our case, x equals to h over r, and n simply equals -1. Okay, so this is roughly what do we have here? 1 plus nx. So again, n is -1, so 1 minus x is h over r. Okay, now work this out. Isn't that equal to negative mgr, then plus mgh? Let me write down mgh first. Minus mgr. Right, now we're getting pretty close to what we expect. We expect only mgh. We didn't expect the next term, right? So we didn't expect a negative mgr. So how do we get rid of that? Well, that's a piece of cake, because after all, the expression for the gravitational potential energy is not just necessarily negative g m1 m2 over r for 2 point masses of distance r apart. You can add a constant. You can add any constant, okay? And the constant that we add in order to eliminate negative mgr, what do you think that constant should be? How about positive mgr? We like that constant to be equal to positive mgr. It could be any constant we want, right? So add that constant, add that constant, add that constant, and then these two cancel. You are left with mgh. Wow. So what we did is consistent. What we know was what we know before from, chapter 7 and chapter 8. Okay, so ug is roughly near the surface of the Earth. Okay, so these two very different looking expressions actually reconcile near the surface of the Earth. So this is a special case of this general expression. And this special case does not work very well if the altitude becomes high, so that h is comparable with r or even greater. All right, so let's go back to this general expression, because when we launch a rocket, we don't expect to always stay close to the surface of the Earth. So when it comes to the gravitational potential energy associated with an object that moves pretty far from the surface of the Earth, such as a rocket, we have to use this general expression of negative g m1 m2 over r. And by the way, we use the Earth here for illustration. It doesn't have to be the Earth, okay? Just basically any 2 point masses, okay? The force of gravity, the work done by that force, you can always calculate that way, and the gravitational potential energy between 2 point masses, you can always write like that. And you can, of course, also change the point mass to a uniform sphere. Remember, that's Newton's shell theorem. As long as the second mass does not penetrate into the first one, so stays outside. Therefore, you can treat the force as that between 2 point masses. You can shrink the surface. You can shrink the Earth or any spherical object, uniformly distributed spherical object, to its center. That's Newton's shell theorem. So whatever we did here still works. Okay, now let's take a look at a real life example. Okay, if you have this much negative potential energy, right? Assuming that you take the constant term to 0. Okay, when you take the constant term to 0, then you have ug. You would have ug equal to simply negative g m over r on the surface of the Earth. If you take that term to 0, okay, that constant term to 0. So it is a very negative potential energy. The reason why it's negative is because you look at where the 0 point is for the gravitational potential energy. If we define the constant to be 0, okay, where is UGR equal to 0? Where is the 0 point? The 0 point is no longer at the surface of the Earth. If you set the 0 point of the gravitational potential energy at the surface of the Earth, you will be needing this constant here. Okay, If we set a constant be 0, then where is the 0 of the potential energy? Well, you just set UGR, this is on the surface of the Earth, UGR, which is equal to negative GMM over R as 0, right? You want to set the UGR is 0, and what is R equal to? R approaches infinity, as you can see here, right? So instead of choosing the surface of the Earth as the 0 point of the gravitational potential energy, you are choosing the potential energy to be 0 as the object is infinitely far away from the Earth. Okay, so imagine a very, very distant object, such as an asteroid flying towards the Earth, is very, very far from the Earth, and at that point we set the potential energy to be 0. Okay, now as it gets closer and closer to the Earth pulls it in with attractive force, right? So clearly the gravity of the Earth does positive work, and in doing so, the Earth has to spend potential energy. You start with 0 potential energy, that's what we define to be 0, when the distance is infinity. So as it lands on Earth, clearly the potential energy is going to be negative, right? But in return, it's got positive kinetic energy, so it crashes onto the Earth with a large speed. So that makes sense. Now, using this as our convention, that is, we can set R equal to infinity as the 0 point of potential energy. Can we use that to find the escape velocity of an object from the surface of the Earth? I mean, you don't have to use that convention, but that just makes the calculation a little bit easier. So what we have here is an object, say a rocket. We launch it from the surface of the Earth, okay? Now, what is the initial speed of that rocket so that it can go all the way to infinity? It can totally escape the gravitational pull, the gravitational trap of the Earth. You know it's going to be a very high speed, right? You know it's not going to be just a few miles per hour, or even 7.9 kilometers per second. That is very fast, but that is only enough for this thing to move around the Earth. It is still not enough for this thing to totally escape from the Earth. You will need greater speed. So how do you find that escape speed or escape velocity? Well, the force is variable, right? As it moves from the surface of the Earth to infinity. So you don't want to deal with a variable force using F equals ma unless you have to. However, we know the only force that's doing work on this object as it flies from the surface of the Earth to infinity is gravity. And that, of course, is a conservative force, meaning we can use what? Conservation of what? Conservation of energy. Okay, so E initial equals E final, and initial is on the surface of the Earth, final is at infinity. Okay, E initial equals E final. This would be the easiest way for us to find the result. Okay, so initial is K initial plus UG initial, right? UG initial. And the final energy is K final plus UG final. Okay, K initial is 1/2 m V escape squared. Isn't that what we're looking for? V escape. Okay? And UG initial, what is that equal to? Well, that equals this, right? If we think of the 0 point of potential energy at infinity, okay? Negative G times the mass of the Earth times the mass of the object divided by the radius of the Earth. So minus G, mass of the Earth, mass of the object over R. What is that equal to? K final plus U final. K final is whatever kinetic energy it still has as it reaches infinity. The smaller the initial escape speed, the slower it goes because the less energy it has when it reaches the infinity. But we're looking for the smallest possible initial speed so that it can barely escape to infinity, right? So by the time it reaches infinity, it's barely moving, right? Otherwise, it would take more, extra initial kinetic energy to make that happen. So we're going to set the final kinetic energy to be 0. Okay, so it is able to get to infinity, but it has lost all of its kinetic energy on the way there. The final potential energy is what? It's also 0. Isn't that true? Because look, this expression here, when R equals infinity, the potential energy is 0. That's how we defined the 0 point of potential energy, right? So the right-hand side is simply 0. I can easily solve for V escape. So V escape equals to, what is that equal to? The square root of 2g times the mass of the Earth over the radius of the Earth. Okay, now you recall the speed it takes to go around the Earth in a near Earth circular orbit is the square root of gm over r. There's no square root of 2 here. This extra factor is what it takes for it to escape the gravitational pull of the Earth entirely, not just going around the Earth, but going infinitely far away from the Earth. Okay, so what is that equal to? Now we can plug in the value of g and plug in the value of m and r and so on, but we can also make the job a little bit easier numerically by rewriting this as 2 g r. Because g is the acceleration of gravity equals big G times mass of the Earth over r squared. Okay, as you can see here, right? So that just makes our job a little bit easier. You don't have to even use the value of the big G anymore, just radius of the Earth, which is 6,400 kilometers, and then the value of G, which is 9.8. So you can easily do that. 9.8 times 6.4 times 10 to the 6 meters, and the answer is about 11.7 kilometers per second. Okay, not per hour, per second. You compare that with with the speed needed to go around the Earth. That's 9.7 kilometers per second. This is 11.2. Okay, this is 11.2. So this is even faster. So we got that from the conservation of energy. So that's another example of the power of the conservation law at work. All right, now let's look at a real life example. If you want to launch something into an orbit, okay, you have to use a rocket to give it energy. What the rocket does, it burns fuel to convert chemical energy into kinetic energy, so that you can send this thing into the orbit by overcoming the negative work done by gravity in the process. Okay, and we're talking about a lot of energy. So here's a real life example. Consider the Russian spacecraft named Soyuz. It docks with the International Space Station. Suppose you launch Soyuz from the ground, a rocket does the job. How much energy does the rocket has to expend, the minimum amount of energy, so that it can dock with the International Space Station, which is moving around the Earth at an altitude of about 400 kilometers above the surface of the Earth. Okay, well, what you need to do is to find initial energy, and then you find the final energy of Soyuz when it docks with the International Space Station. The difference in energy has to be provided by the rocket. Okay, so let's see how we do that. E initial. When Soyuz is on Earth, we know what that is. There's no kinetic energy. There is only negative potential energy minus G mass of the Earth's mass of Soyuz over the radius of the Earth. Right? We learned that before. Now the final energy, let's see. The final energy equals K final plus UG final, right? Remember, K final is not 0 because it has to move, at the same speed, the orbital speed of the space station. Otherwise, you can collide instead of dock. Okay, so it is 1/2 mv final squared, and then minus G mass of the Earth, mass of the space probe, divided by what? Divided by the new distance between the center of the Earth and the Soyuz. And that would be R plus H. H is the altitude, which is about 400 miles, 400 kilometers. Okay. Now, we know what H is. Do we know what B final is? We do not know what B final is yet. So how do we find B final? Well, it turns out V final is not independent of H. It has to do with the orbital radius. Because look, you're doing circular motion, right? So once again, you can apply the condition for circular motion. That is, there has to be net force pointing to the center of the circle, serving the centripetal force. So you have F, again, you have FC from FG. So you have mv final squared over R. R is actually radius of disk plus h, equals to what? Equals to the gravitational force, which is gmm over r squared. Right? Now, if we cross 1 power of r, then we get mv squared equals to gmm over r. R final, actually. But interestingly enough, the left-hand side, it differs from the kinetic energy only by a factor of 1/2. So if I multiply this by 1/2, then I multiply the right-hand side by 1/2. That's just, the left-hand side simply becomes the final kinetic energy. And the right-hand side also is pretty familiar because, you look at the expression for the final potential energy, the only thing that's extra is that factor of 2, and of course the negative sign, okay? So I can write an interesting connection between the kinetic energy and potential energy for any orbiter or any satellite revolving around the Earth, and that is K equals to what? Negative 1/2 of U. Okay, because U is equal to, as U equals to negative gmm over R. So here you have an extra 1/2 and you're missing the negative sign. Okay, now why is K negative? You say, no, don't worry, because U is negative. Okay, so the negative of the negative is positive. So that means that that the total energy E, I can write as K plus U. But K is negative 1/2 of U, negative 1/2 of U, plus another U final. And that is U final over 2. Now remember, U final is negative, okay? So the overall energy of this space probe is negative, even though it moves very fast with a lot of kinetic energy. There is nothing wrong with that. Look, the overall energy has to be negative. It cannot be 0 or positive. What is wrong if 0 or positive? Look, if it's 0 or positive, that means it is able to reach infinity. It can escape the Earth's gravitational pull, because as it reaches infinity, you have 0 potential energy, right? And you have a either 0 or positive kinetic energy, because your overall energy is 0 or positive. So you cannot allow this object to have an overall energy that's 0 or positive. It has to be negative. That's how you lock it up. That's how you trap it, around the Earth. Otherwise, it's going to escape to infinity. Okay, so that's less than 0. All right. So in our case, so that's our study of the connection between kinetic potential energy of an orbiter. So in our case, I can then find the final energy now. So the final energy now becomes negative G, mass of the Earth times mass of the spacecraft divided by 2R plus H. Okay, okay. We just use this expression. We just copy this result over. Let me write down explicitly the total energy as a function of R. So E equals to negative gmm over 2R, or negative mv squared over 2. You can write it that way as well. Okay, no matter how you look at it, it's negative. Okay, the total energy is negative. So you have the initial energy, you have the final energy. All you have to do is find the difference between the two. So the energy needed to boost the Soyuz from the ground to be able to dock with the International Space Station is delta E. So delta E equals E final minus E initial. Okay, and that is negative G, mass of the spacecraft times mass of the Earth, divided by to radius of the Earth plus the altitude, which is 400 kilometers, and then minus its initial value on the surface of the Earth, which is itself negative. So overall, you have a positive sign, GMM over R. Okay, so you have a negative term and a positive term, but a positive term has greater magnitude, obviously, because it's got a smaller denominator. So you have to plug in some data. So small m is about 9,000 kilograms. Okay, 9 metric tons. 9 metric tons. And h is about 400 kilometers. You know the radius of the Earth, 6,400 kilometers. And of course, the mass of the Earth, you know what that is. And G, you also know what that is, okay? So those are no problem. So you plug that in and you find that delta E numerically is equal to about 3 times 10 to the 11 joules. Okay, so it's about 300 billion joules. But to put this in perspective, just how much energy is that? I mean, you know, it's a lot of energy, right? How does it compare with, say, the power consumption of a typical household over 1 month? Well, we have to first convert this joule to kilowatt hour, because that's the unit we use for in power bills. Each kilowatt hour, it's 1,000 joules per second times 3,600 seconds, so it's 3.6 times 10 to the 6 joules. That's 1 kilowatt hour. And a typical American household uses 557 kilowatt hours per month. So therefore, this much energy, 3 times 10 to the 11 joules, it's equivalent to about 12 years, okay? About 12 years of total power consumption of a typical American household. At 557 kilowatt hour per month, typical American household. That's a lot of energy. Okay, and it's not just the amount of energy that's expensive. It's how you get that energy. You have to burn, fuel, and we're not talking about regular fuel. We're talking about liquid hydrogen, liquid oxygen. It's very dangerous, extremely difficult to deal with. So it's a lot of money, and out of these 9,000 kilograms, only a very small portion of that is actually useful payload. Okay, most of it's just structure itself. So space aviation is very expensive, and we're not even talking about going to the moon or to Mars. Just still near Earth's orbit. All right. Now we have some interesting data to look at when it comes to the energy needed to send something into space. Okay, first of all, the Space Shuttle. The Space Shuttle was first launched in the year 1981, long time ago, and still it remains one of the most spectacular means of reaching beyond the atmosphere. And it is the first way of flying something into space and recycling, getting it back and use it again, reusable gadget. But not everything is reusable. You look at the picture of this Space Shuttle, okay, being launched. This orange thing in the middle, that is the fuel tank. This one right here. Okay. The fuel tank is right here. Sorry, let me make sure more careful. Fuel tank. This fuel tank holds a little over 500,000 gallons of liquid hydrogen and liquid oxygen as fuel. And when the thing is launched, So it outputs at full throttle. It produces 37 million horsepower. Okay, and how much fuel is it burning? It's burning so much fuel that it can empty an average swimming pool in 25 seconds. That's how much fuel it is using. Okay, that's what it takes to produce 37 million horsepower to lift this space shuttle into space, and the weight it lifts is about 27 tons. 27 tons. Okay, you think that's a lot? Yes, it is a lot, but that's still an old program. Is already retired. These days we have even bigger rockets. I have a picture of some typical, famous rockets over the course of the last 70 years or so. You start with the former Soviet Union rocket, and then that's the second one on this. Actually, it's not listed due to with chronological order. It's just due to the size. Here is the second biggest one on the list. That's simply called Falcon. It's Falcon Heavy. It's made by SpaceX. Okay, and you have another Russian rocket and a Chinese one, and a couple of like 4 US rockets, another Russian rocket. The biggest one on this list is the Starship. The Starship is being developed by SpaceX. Okay, by SpaceX. It is the world's heaviest rocket and also the largest. It's got a height of 120 meters. Okay, and has a payload of 150 tons. You compare that with Space Shuttle, which is 27 tons. So this is about 5 times. The capability of lift is about 5 times as much as the enormously powerful engine of the Space Shuttle. Okay, what can this Starship do? Hopefully, well, here is a beautiful artist rendition. Hopefully, this is what you're going to find on the surface of the moon in the later part of this decade, late 2020s. Starship on the moon, and you can see how small people are in comparison with this rocket. Let me expand this picture for you. Look at how small this is. See these two people here? That's how small it is. Okay, it compared with the size of this rocket. So it's an enormous rocket, and we have the rocket already being built. So we're looking at an exciting era of space aviation into back to the moon, and then human space mission to Mars and even beyond. All right, so and here's a picture of the Space Shuttle in comparison with the Starship. They don't look like different in size, but don't forget this Starship. We're only looking at part of it, only looking at the top part of it. Okay, in this diagram here, it's only this part. It's only this part. It does not include the first stage, which is even bigger. Here's the first stage. It's omitted from this picture here. Okay, so it's actually much bigger than the Space Shuttle, which is also already very, very big. All right, so I hope you find these interesting. And there's a saying, this is no rocket science, right? But here we can proudly say this is rocket science. Okay, so we're looking at the basic theoretical foundations of modern rocket science. So in the next lecture, I'm going to continue with a discussion of gravitational potential energy, and we're going to use that to examine the physics of an old movie called Armageddon. I love that movie, I still do. And what is wrong with the physics though? Well, it's going to be something interesting to analyze. We'll see that in the next lecture.